Hi everyone, this video is intended as a follow-up to the lab activity in which you took ice, put it in a beaker, put a temperature probe in it, fed the temperature probe to your calculator so you could watch the temperature versus time plot develop. You put that beaker of ice on top of a hot plate and you slowly warmed it, and you watched as that ice converted to liquid water and then to steam. And on your calculator you have a heating curve, and that has a particular shape, and the purpose of this video is to analyze that shape both from why there are the plateaus that there are and calculate the heat along the curve. So let's go. Hopefully, as you did your lab, you have a plot that looks like this. Your temperature response over time. If this is 0 degrees and this is 100 degrees. I would love it if your ice was a little below 0, but it's hard to accomplish that. But hopefully you saw a plateau first. As all of the ice is melting, it holds at 0. And then you get a ramp up to 100 where it plateaus again as it boils. And then it hopefully will go above 100. The key thing that I was hoping you would see are the two plateaus. And you know that this was the phase change time. This is where it melted, and this is where it boiled. And so somehow we have these plateaus at phase changes. The key thing I want you to realize is that all of the energy you're adding, and you were indeed adding energy because your beaker of ice is sitting on a hot plate, all of the energy was consumed in breaking IMFs. These plateaus are associated with phase change times where IMFs are broken. And we're going to learn in this video how to calculate the heat change as we increase the temperature. That's Q equals MC delta T, which you've done before. But as we go through phase changes, we handle that a little differently because that's IMF breaking time, and we're going to do the calculation based on the material that we have. One of the other things you might have noticed is that this plateau is longer, and I didn't really necessarily draw it that way. This is a longer plateau than this one because it always takes more energy to boil than it does to melt. If you look at this next chart, we consider from the kinetic molecular theory what we're doing. When you're in the frozen state, all of the molecules are locked in position and they have strong IMFs between them. You are allowing them to free from those chains, so to speak, and to be more movable. However, they're still close to each other. So they haven't been given tremendous energy of movement, but the IMFs have been loosened. And so that takes less energy than in the boiling and condensing phase where we have this complete independence gained by the molecules. So it always takes more energy to boil something than it does to melt because boiling requires complete breakage of all IMFs and much higher movement for the molecule. Alright, we're going to now go through the calculations of the heat required to do these changes, and then I'm going to go backwards on the curve and do a cooling curve. Here's the heating curve, and the question you're asked is to calculate the heat required to convert 25 grams of ice beginning at minus 25 degrees Celsius to steam. What is steam? Vapor water, right? It's still water at 125 degrees C. Alright, so the way we do this is to break it into sections. All of the slanted times are handled by Q equals MC delta T. Do you remember that from our chapter 3? That's the warming heat. The slants are when we're warming it up. See, this is all associated with temperature change. When you're at a plateau, there is no temperature change then. The temperature is constant. But if you're at a slant, that's a warming time. So this equation applies. This is warming time. To take a mass of water up a certain degree ramp. It depends on the specific heat of the material. Remember, C is the specific heat of the material. So we're talking about water, ice to steam, and liquid water in the middle. Okay, and let's mark that on here. We are ice over here, and we are water from this point. We're 100% water at this point. On this plateau, we're a mixture of ice and water. We're water all the way through here, and now we are 100% steam. In this section here, you have a combination of liquid water and steam. So our calculation for this, I'm going to write it above so I have some space for other things, is 25 grams is my mass. Do you remember the specific heat of water? It's 4.18 joules per gram degree C. And what's my temperature change? I'm going from minus 25 to 125. That's 150 degree temperature ramp. And when you multiply this out, you get 15,675 joules. But I'm going to convert that to kilojoules because you're going to see the next figures are in kilojoules. Okay? Okay, 15.675 kilojoules. That takes care of all of the slanted sections. Okay, these are accounted for. And now we're going to finish this up with calculating the heat required to break bonds break IMFs, I should say, in the melting phase and in the boiling phase. And these have to be handled separately. They're two different heats. The first one that we're going to look at is the melting heat. And this is given the name the heat of fusion. The heat of fusion for water is 6.02 kilojoules per mole. Okay? I look it up in a table. It takes that much heat to melt a mole of ice. Okay? It's a positive number because I have to input heat to do that. It is what we call endothermic. And I need to figure out how many moles are in 25 grams. So I could do a little molar mountain here, and I could do 25 divided by 18. I'm going to get 1.39 moles. Okay? So I'm going to multiply this by the number of moles I have. And I'm going to determine it's going to take 8.36 kilojoules to melt that. That's melting. Thirdly, I'm going to look at boiling. This is called the heat of vaporization. And as I said earlier, it's a bigger number because it always takes more energy to boil than it does to melt. Now on a table you'll see this number is related to the temperature. So there's a boiling at 100 degrees, which is what we're doing. There's also a heat of vaporization at a lower temperature. You could only accomplish that if you were at a different pressure. So at ordinary conditions, we're used to water boiling at 100 degrees. This is the number you will typically use. Oh, this is 40.7. And then this is 1.39 moles. And you'll get 56.6 kJ. So the grand finale of this is to sum these up. I need that much to warm it up, I need this much to boil it, and I need this much to melt it. And so the grand total, the sum of all of this, the sum equals 80.6 kJ. It takes that much heat to take ice at minus 25 to steam at 125. Let's do the same approach, but we're going to work in reverse. And so It might seem odd, but we're going to take it backwards into a cooling curve. When we do this, all of our heats will be negative because it will be exothermic. Here's your problem. Calculate the heat release when 50 grams of acetone vapor. I picked something other than water so you could try some new numbers and see how this applies to other compounds. When 50 grams of acetone vapor at 100 degrees is cooled to 50 degrees, you're given that the boiling point of acetone is 56. You're going to have to adjust your thinking because not everything boils at 100. That's a water property. The heat of vaporization, which is going to be involved because we're crossing through a phase change. You see the temperature range of 100 to 50 encompasses a phase change time, so there will be a plateau. We need this phase change heat, so that's given. And then we have the specific heat for the material given here. So let's draw a picture before we do this calculation. We start at 100, we end at 50. And I would just draw this in advance. We know there's a plateau at 56. That's the condensation time. I'm going in reverse, so this is now condensation. It's all acetone vapor, cooling to 56, and then cooling further to 50. So we see we have to handle this in two chunks. We have the cooling heat from 100 to 50. The Q equals mc delta T will be that range. Q equals mc delta T. My mass is 50 grams. The specific heat of this material is 2.15, and I have a 50 degree temperature range. That turns out to be 5,375 joules. It's joules on the specific heat in contrast to kilojoules on the heat of vaporization, right? So we need to switch this to kilojoules before we sum them. Okay, kJ. And now we have to add the other piece, which is the phase change, the condensation heat. This is now going to be handled. It's still the heat of vaporization, but it's also the heat of condensation. It's the same heat released as the vapor cools down. It will just be negative. Okay? And we have to figure out how many moles this is. This is acetone. It has a molar mass of 54 grams per mole. Okay? So my molar mountain is going to be 50 over 54. That turns out to be 0.93. Okay? So my condensation heat will be 29.1 kJ per mole times the 0.93 moles, and I get 26.9 kJ. Wrap this up by summing it up. The sum of the heats, this is the summation sign, the sum of the heats is 32.3 kilojoules, but because this is all cooling, I'm going to change it to a negative. Now, I usually just adjust the sign at the finish because I know a cooling curve is an exothermic thing, and so I indicate that at the finish. So that is the reverse thinking, and I now have a different kind of heat for you to consider.
The Miami Heat are currently sitting on an NBA best 10-game winning streak as the Heat take on LeBron's old team, the Cleveland Cavaliers. That's Kyrie Irving's team now, though, as they head into town. First quarter, and it's LeBron attacking the rim. D-Wade, the alley-oop. Tyler Zeller can't get back in time, and LeBron throws that one down. He was 10 of 19 from the field. He had 28 points, 8 assists. No assist on this one. It's another LeBron steal and jam, and again, nobody tracks him down from behind. LeBron throwing it down. The Heat up early, 23-18. Still in the first. Shot clock winding down. Watch Mario Chalmers from deep bury that shot. The Heat finished the quarter on a 14-2 run. Second quarter, Dion Waiters goes behind the back and drives for the reverse layup. He had 12 points at the half. The rookie from Syracuse playing some good ball. Udonis Haslem ahead to Mario Chalmers. Over to LeBron James. That's a Heat transition bucket They led it big at the half by 18-point. Third quarter action now. C.J. Miles starts warming up for Cleveland. Buries a three there.